So first of all, I'd like to start by thanking Gareth and Uli for the invitation to come here, and Stefan for all the work answering all the emails and organizing everything. So thank you very much. So I'm going to tell you about the work that my colleagues and I have been doing, as you said, on the structure and reactivity of water and carboxylic acids, acetic acid in this case, on TiO2 model catalysts. So I'll start with just acknowledging the people that I work with, a lot of people in particular. I'm not going to call them all out, but Zdeněk Danalik and Nick Petrick, longtime collaborators at PNNL. The theory work I'm going to show you today is mostly with Annabella Saloni and one of her students, Jeon Zhu, and then some earlier theory work with Chris Mundy and Marcel Baer. Okay, so real quick outline. I'll just give you one slide motivation, one slide for the experimental approach, and then I'll have three topics. Two of them are the structure of water on anatase 101. One's the structure of water on rutile 110, and then talk about some recent work that we've been doing looking at the reactions of acetic acid on anatase, where we use both single crystals and shape-selected nanoparticles to look at the reactions. Okay, so one slide motivation. Water's everywhere. As I promised, Stefan, there's an interstellar dust cloud. In fact, amorphous solid water might be the most prevalent form of water in the universe. It's obviously important on Earth. It's important in geology, atmospheric science, technology. A lot of these have interfaces. Water at interfaces, I don't have to tell you guys, is pretty important. And that's generated a lot of basic science interest in it, and that's what I do, model systems mostly, right? Most of the work on single crystals. So in a lot of audiences, this needs a lot of introduction, maybe a little bit less so in this audience. The tool I'm going to show you most today is using infrared spectroscopy on a dielectric substrate. So unlike most people are familiar with infrared spectroscopy on a metal surface, where you have the surface dipole selection rule. So you can only see transition dipole moments normal to the surface because the conductor screens out any transition dipole moments parallel to the surface. That's not true on a dielectric substrate. You can see those vibrations both parallel and perpendicular to the surface. You do pay a price. Nothing comes for free. The absorbances are maybe a factor of 30 smaller than you have on a metal. So you have to work at it a lot harder, or you have to be very clever like you guys are and build a much nicer instrument than what I have. So a couple things about infrared spectroscopy on a dielectric substrate that are different. You get S-polarized signals. They're negative. They're always negative. They look like emission features. It's just an interference effect. And they're equal to the product of the real times the imaginary part of the index of refraction. The p-polarized signal, okay, so maybe let's take a step back just for everybody who's on board here. S-polarized means your electric field vector is in the plane of the surface. P-polarized means it's in the plane of the k vector coming in. So if you come in at glancing angle with a p-polarized light, you have an electric field component that's perpendicular to the surface and along the surface in the direction of the beam, okay? And you see both of those, and they come up with opposite signs in some approximations, right? And so you can have both positive and negative features, and it turns out that positive features are going to correspond to vibrations that are in the plane of the surface, and negative features are going to correspond to vibrations that are normal to the surface. Now, as you know, TiO2, both rutile 101, rutile 110 and anatase 101 are highly anisotropic surfaces. Water, it likes to have directional bonding, so you get very anisotropic structures. In that case, it makes a lot of sense to do your infrared spectroscopy two different ways, where you bring the light in along the rows or perpendicular to the rows, and you do two polarizations, S and P. So for most of the coverages, we'll have four spectra, two S polarized, two P polarized, along the rows and across the rows. And what I hope to show you is that can give you a lot of information about the structure of the water adlayer and other adsorbates on the surface. Okay, P-polarized signals are a little harder. Basically what I'll show you is we're gonna fit the spectra, the observed spectra, to get the imaginary component of the dielectric constant, which of course is the absorbance, right? Okay, so the experiments I'm going to show you are on clean, well-characterized single crystals, at least for the first part, of anatase and rutile. We're going to work with D2O because it turns out the spectra is a little cleaner in the D2O region of the IR than it is up in H2O. And and we're going to absorb water at the highest temperature we can for the coverage that we want to get, so we give the water a chance to find its equilibrium configuration to the extent possible, and we'll cool it down to 40 Kelvin and do the IR spectra. Okay. So my goal right now is to convince you that we can take a series of spectra like this. These are 4 spectra for 1.5 monolayers of D2O on anatase 101, and you can just see there are peaks and bumps all over the place. And I want to convince you that we can take this information and learn something in detail about the structure of the water adlayer that produced that spectra. Okay, so we're going to remind everybody what the surface of anatase 101 looks like. From the side, it's a sawtooth kind of structure. You have 2-fold coordinated oxygens running along rows, the titanium 5-fold coordinated sites. Those are the strong binding sites for the water. They're going to act as anchors for the water adlayer. They're kind of like the immovable parts of the water film. The monolayer on this surface has about 5 times 10 to the 18th atoms per centimeter or per meter squared. And I'm going to show you the plan view 2 things. One, the 101 bar direction is perpendicular to the row, so we'll bring the IR beam along those one time. 010 is parallel to the rows. Okay, and these are the 5-fold coordinated titanium sites here. The key point here that I'm going to bring up is going to relate to the structure is that this distance, about 3.8 angstroms, is a bit long for hydrogen bonding, right? So that's going to affect the resulting structure. Okay, so as you might expect, if you're going to talk about anything TiO2 here, Uli probably did the first stuff, and certainly often the best, almost always the best. So this is Uli's images of water monolayers, water monomers at low coverages on anatase, and she worked with Annabella Saloni, who, again, if you're going to do theory, she's the go-to person. And basically what happens is the water absorbs on the 5-fold coordinated sites, and then it adopts this parallel geometry, or this symmetric geometry where the 2 hydrogens are pointing to the adjacent oxygens on the row. Okay. If you go to a monolayer coverage, you get this Annabella calculated 20 years ago or so, DFT, 0 Kelvin structure. You get these, the water monomers, they rotate because if they're all lined up, the dipoles all line up, and so you can minimize the dipole interactions a little bit by doing this rotated structure. She also calculated, Annabella Saloni calculated, again, 0 Kelvin structures at 2 monolayers of water on the surface, and I'm going to take a step back. Anatase and rutile are a little funny in the way they define a monolayer. They define a monolayer based on the number of these titanium 5-fold coordinated sites. If you fill those up, you've only filled up half the surface. An ice layer has 1.1 times 10 to the 19th molecules per centimeter per meter squared. So 2 monolayers of water on these rutile and anatase are really one monolayer of water, just so you know. So this is 1 monolayer of water, but for historical reasons it's called 2. What she found was that there are a number of closely related structures, or structures that are close in energy, and so the suspicion would be that in a real situation you're going to populate several different structures. And we think that's what's happening. Okay, so now we're going to do this experiment. Here's the IR spectra, S polarized along the 2 azimuths for 1 monolayer of D2O on this surface. Couldn't be simpler. Basically, there are 2 peaks, right? Tells you right away that there are 2 transition dipole moments that are the dominant thing in this spectra. You do the P polarized spectra, you see the same thing. 2 peaks, they're positive, right? And they're more or less the mirror images here. And it turns out for this, if you do the Fresnel equations for the system like this, if you have a system where the transition dipole moments are all parallel to the surface, you will see this symmetry in the spectra, right? Okay, so that tells us we have basically a flat water monolayer. There's not really any hydrogen bonds pointing up or down. And this was Annabella's calculations from a long time ago. Well, guess what? There's like 2 oscillators there. Okay, those are the 2 oscillators across the row and along the row, more or less. But they're not quite, and I'll go over that next. Okay, so now what do we want to do? We want to be a little more quantitative than that. Okay, so you solve the Fresnel equations for a 3-layer system. I'm not going to show you the equations, they're ugly. All we do, we just put in, we just regress, sorry. We just solve for a fit, we just fit the equations with the imaginary component, and then of course you use Cramer's chromate to get the whole dielectric constant. So the smooth lines here are fit to the data. From this, now we have the K vector, the K, with 3 components. Along the surface in one direction, along the surface in the other direction, and normal to the surface. So we can reconstruct the vector for the transition dipole moment that gives these things. And so now you can just say, well, I'm going to take, if I take in the plane, the ratio of those and those gives me the angles, right? So my postdoc Chris O'Connor, who did this data, and he's the one that realized he could do that, he did those calculations, and these lines here are his calculations of those angles. It's not very bad, right? It's kind of tells you what's going on there, right? So we went to Annabella Saloni and we had this data, and I had the more complicated data that I showed you, which is a little harder to interpret. And we said, Kate, are you interested? You want to update this? And she was. So she worked with her student, and they used SCAN functionals, and they did simulations down where they ran it at 400 Kelvin, and then to kind of equilibrate it on a DFT calculation type scale, and then quenched it and calculate the IR spectra. So there's their calculations, there's our data. Really, the agreement's really quite good. Again, in the calculations show that it's all very flat, and basically, because it's a real system, it's not quite as ordered as the 0 Kelvin stuff. But basically, you see these water molecules sitting on the titanium 5-fold coordinated sites, kind of pointing across the rows and along the rows. So that's the picture for 1 monolayer. Again, half the surface is sort of covered there. Okay, so back to this one now. So this is 1.5 monolayers. It looks considerably more complicated. But you can start right away. Because we know, again, where the electric field vector is for these, this is a bond that's across the row, right? So it's hydrogen bonding across the row. It's a very low in frequency. That means it's a very strong hydrogen bond. So we have a strong hydrogen bond that goes across the row. These negative peaks in the p-polarized spectra, those are hydrogen bonds that are normal to the surface, okay? Medium strength. And then there's a bunch of stuff over here, okay? Weaker, very weak, almost non-hydrogen bonds normal to the surface here. So we can do the coverages. We did 1 monolayer, I showed you 1.5. We also did 1.3, 1.7, and 2. And now again, these are the imaginary part of the dielectric constant across the rows, along the rows, and normal to the surface, right? And you see there are very consistent trends in how these things are developing as we go along, okay? So Annabella did the calculation for a big unit cell. What I want to point out here from the side view, you can already see in this simulation that there are regions where you're getting like 3D hydrogen bonded structures. There's a whole bunch of different things going on here. That matches with our earlier calculation, the 0 Kelvin calculation, that said that there were a number of configurations that were very close in energy, okay? They can calculate the IR spectra for that simulation. That's here, and you can notice there are some really strong similarities. There are the strong hydrogen bonds across the row, all right? There's these other hydrogen bonds in the intermediate range, these peaks here, and we get the stuff up over here. Okay, now the great thing is that the theorists can do some very specific things. First of all, they can go in and look at various things. So within that big unit cell, if you look at it long enough, which her student did, you see there are a lot of what we call dimer motifs, and I've circled a few of them here. Well, you can't see that very much back there, so I'll blow it up. And so what the dimer motif, and this is the thing that's going to give us the strong cross-row hydrogen bond. You have a water molecule that's binding through a titanium site, through its oxygen lone pair. That's a strong bond, and it points towards the water molecule that's bonding to the bridging oxygens with the hydrogen down, and it tilts over a little bit, right? And that's one of the dimer configurations, right? So those are one and 2, right? And now what they did was they said, well, we're going to take a unit cell and we're going to put everything in that dimer configuration. We're not going to raise it up to temperature so it populates other things. We're just going to keep it in the dimer configuration and calculate the IR spectra from that. And that's here, right? And again, this is just what we saw in the experiments. Those are the strong cross-row bonds right there, right? That's what gives us this low temperature feature here. these hydrogens that point down, right, towards the bridging oxygen, that's what gives us these two peaks in the middle. And then these ones that point along the row, right here, are the ones that are responsible for that up there. So you're really starting to pick out in some detail what the structure is for this water adlayer. Okay, and again, here's the overall agreement is really quite good. So one thing that I haven't mentioned is anything about dissociation. So there's been some reports in the literature that water might dissociate at the anatase interface, 101 interface. There's some SFG spectra that was out here is like this, right? That I think Ellen's here, yeah. And the question is there dissociation there or not? And Annabella Saloni looked at, did the calculation of this, and her take on it was that you couldn't tell one way or the other. So from that either were consistent. Well, I'm going to show you water, not with the water adlayer on top, and so I don't know really what happens when you have a whole bulk layer of water there, and the story could be different. But if you have non-hydrogen bonded water molecules on these surfaces, they stick out like a sore thumb. This is the spectrum from a rutile 110 surface. It had about 7% vacancy. So when you hydroxylate that, you maybe have 14% of a monolayer. And it's just real easy to pick up because all that oscillator strength goes into a very narrow peak. What we saw, I didn't point it out, but there was another peak in the original 1 monolayer spectra that I was showing you. It was right up here, right? And that is the bridging hydroxyl peak for the hydroxyl dangling OD for a dissociated water molecule. We were estimating it was 2% maybe on ours. And we did Uli's trick. We could, in a different paper, you can irradiate the surface with electrons, make more vacancies, dissociate the water in that so you get a clean signal. So that's what we're showing here. So we kind of know where the OH on this surface was. And so we were seeing maybe a few percent vacancies. And this was a lightly reduced crystal so far as we know. And with the experiments, you get the crystals are natural crystals, and so there can be variability in that as well. Okay, so now I just told you about the structure of water on anatase, and now I'm going to compare to some earlier work that we did for the structure of water on rutile. And what I'm going to argue is that this distance here, which was 3.8 angstroms on this surface between the titanium 5-fold coordinated sites, is 2.95 angstroms on this surface. And you promote hydrogen bonding here that you don't here. The number of titanium sites per square meter is the same to within 5% or something on these surfaces. It's the same number. It's 5.2 plus or minus a little bit times 10 to the 19th. So it's not like there's more or less. It's just a different spatial arrangement. But that's going to lead to a different hydrogen bonding configuration in the water adlayer. It's really quite different. So this is some earlier data from 2012. It's the same thing. I'm showing you 1 monolayer of D2O and now on rutile 110, 4 spectra, S polarized and P polarized, along the rows and across the rows. Didn't do as much averaging on this data as the ones we were showing you for the anatase. But it's basically what we see is there's a peak here at high frequencies that corresponds to hydrogen bonds along the row. There's a little bit stronger bonds that are hydrogen bonds across the row. Here's this, so Chris Mundy and Marcel Beer did the calculations for what this structure is that maps on well here. What I want to point out here is you can look at the side. First of all, this is a flat hydrogen water layer. Everything's more or less in the plane. If you see here, this is the string of water molecules that are bonded to the titanium 5-fold coordinated sites. They form weak hydrogen bonds along there, right? And then the extra hydrogen points to the bridging oxygen row, and it goes either way. So that's what you're seeing from the side, okay? When you go to 2 layers, right, oh, no dangling bonds, right? When you go to 2 layers now, so that's 1 full layer of water on the surface, it's the same kind of picture. That the first, you still have the water molecules, hydrogen strong through the oxygen lone pair of the titanium. They're still forming a hydrogen bond to the neighbor. The one that would be pointing at the bridging oxygen now points up, and it forms a hydrogen bond to the water molecules that are now in the second layer. One of them has the hydrogen is putting its hydrogens down to the bridging oxygen, forms a bond there, and it forms a weak bond along the row. And if you look at it from the side, you basically have these these strings that form along the surface. And there's no network that has kind of a 2D like across the surface like there was for the 2 monolayers of water on anatase. And the distance here is too long, right? So you took a unit cell that was a little more square on anatase and you squished it and made it a little longer on rutile, and so it promotes strings as opposed to a 2D hydrogen bonding network. Okay, so that's summary for that part. Basically, hope that just doing this azimuth and polarization resolved spectroscopy along with some MD simulations of the water structure can provide quite a bit of information about these water adlayers. As I said, the 1 monolayer in water, it forms, basically they're isolated water molecules that are somewhat rotated. You get this hydrogen bonding network that develops at higher coverages, and it's highly anisotropic, but it's really templated by these strong anchor points within the water layer to the titanium sites. Whereas for the rutile 110, the slightly different geometry promotes these strings along the surface. And I don't show it here today, but this leads to a significant amount of restructuring then when you add more water on top of it. Okay, so now I'm going to switch gears and I'm going to talk about a little chemistry, acetic acid reactions, and we're going to do experiments on single crystals, and then we're also going to use shape-selected nanoparticles of the same anatase surface. So my goal here is to convince you that reactions involving ketene can be important for making acetone when you start with acetic acid. What I'm showing you here is a reaction scheme that's in a paper that we've submitted that Jayan and Annabella calculated for this. And I'm not going to go through this in any detail. What I want to convince you is that this scheme is the one that's preferred in the literature. This is the one I'm going to argue for. On the other hand, as we got in the introduction, I'm a physicist. My last and only chemistry course was freshman chemistry a year before Gareth was born. So when I look at this reaction, I think, oh my God, how have I strayed so far into chemistry? But here we are, and I was a little comforted because I found out that a lot of you guys are physicists too. So maybe I won't get the chemistry questions that I won't be able to answer. Okay. Anyways, so I think the preferred carbon-carbon coupling reaction for this that people believe happens is the so-called beta-ketoacid mechanism. And the idea is that you drop your acetic acid on the surface, and I think a common step for all of them is they go through this enolization where the methyl group comes down and drops a hydrogen atom onto the surface. You bring another acetic acid in there, you do the carbon-carbon coupling reaction, and you get this beta-ketoacid, which then goes on and falls apart. And you don't know how many times I had to stare at those and try and remember what words to say for all those little things up there. I'm just going to tell you, it's pretty scary. So the key point is all these reactions happen on a single particle. Not surprising, it's all local chemistry, right? A ketene mechanism is also out there in the literature. It's, again, goes through this enolization step, but you also drop the hydrogen off, you form a ketene. The stuff that was in the literature, I think, mostly was then imagining that the ketene reacts locally. But if the ketene desorbs, right, then it could be transported to another particle and do chemistry that way, right? So we've done a lot of work characterizing the bonding geometry of formic acid and acetic acid on the surface. I'm not going to show you a lot of that right now. I'm just going to ask you to trust me that we've done a lot of it. But what I'm showing you is cartoons for that summarizes it. In the gas phase, these things come in as dimers. They fall apart on the surface. They can adsorb in a molecular form. This is showing you for the formic acid, but just replace this with a methyl group for the acetic acid. It can form a molecular acid that binds to the titanium sites and then to the bridging oxygen rows. It can drop the proton down and form this bidentate. That's a little more strongly bound species. You get both of them at higher coverages. They're both there, and that's supported by DFT calculations. Again, we've done a lot of work on it. I love these STM images. You can tell because you have a fuzzy STM image. That's the one for the molecular acid because it's on the titanium sites and the hydrogens are flipping back and forth. You get a nice smooth one. That's the one that's the bidentate. In infrared spectroscopy, you can actually see the CO stretch for the molecular form. You can see the asymmetric stretch and the symmetric stretch for the bidentate form. And again, DFT calculations are consistent with this, that particularly as you move up in coverage, you could get both the molecular and the bidentate form. So on a single crystal in an ultra-high vacuum system, when you heat up, you expose it to you expose it to acetic acid, and you just start heating it up, and you watch what comes off with your mass spec. What comes off is water desorbs at low temperatures, 250 to 400 Kelvin, and ketene desorbs at high temperatures. You don't see any acetone. You do see a little bit of recombinative desorption. The acetic acid comes off at high temperatures, 550 to 800 Kelvin, in a fairly broad line shape. This is showing you here the water yield. It comes up and saturates at a half monolayer. The ketene yield comes up and saturates at a half monolayer. Okay, so no carbon-carbon coupling reactions there. And this is what got us thinking about. One of our postdocs was like, why, they see acetone production on anatase and particle beds. We don't see it here. What's going on? So they had the good idea where they said, well, we're going to take, we have colleagues that make shape-selected nanoparticles, anatase 101. This is an image of particles that we sprayed onto a metal surface, a gold-coated metal foil, of these shape-selected nanoparticles. And if you zoom in, you'll see they all look exactly like that. I mean, trust me. No, but we've done a lot of work characterizing these things, and they predominantly expose the 101 facet. And of course, they're not perfect. And from a surface scientist guy who's always worked on single crystals, when they showed me this SEM, I was like, oh my God, we're going to do experiments on that. But it's going to be in the same chamber where we do the single crystals things, and that's the nice thing about it. And so the idea for the experiments was, well, you could take a gamish like this, and now you could start exposing it to acetic acid or whatever reactant you want. And if you could do it in the conditions where you can allow the reactant to kind of work its way down into your particle bed, then you could start now heat it up again and see if anything different happens. And of course, I wouldn't be up here telling you about it if everything was exactly the same. So the first thing, like I said, we did a lot of characterization. Yang Wang and his group were the people responsible for fabricating these particles. But I'm not going to tell you about that. I will show you a little bit of the chemical characterization, which for me, since I love water, water is my favorite thing for characterizing how good my surfaces are. So the adsorption of water on anatase is well known for years and years. For those of you who don't remember, I've reproduced a very squished version of water TPDs down here from the single crystal surface. But basically, there's two peaks. There's a titanium peak, an oxygen peak, and then you start to form multi-layers down here. So now what we're going to do is we're going to take that particle bed that I showed you on the previous slide, and we're going to expose it to D2O at a temperature where we can't build up multi-layers, right? You can build up a monolayer and two monolayers, but not multi-layers. And we're just going to dose it with more and more D2O, and then we're going to do a TPD afterwards. And the thing that shocked me personally is that the peaks line up almost perfectly. It was really surprising. But the point is we could load in a lot more D2O in here. We got about 90 monolayers equivalent of D2O into this film, okay, into this particle bed here. Go back into that particle bed when we desorbed it, and it all comes out. And you see there's this interesting thing, right? Because the relative ratio of the titanium 5-fold coordinated to the bridging oxygens is changing. And there's some complicated ways. So the molecules come in, they populate something, they saturate the surface that can see the molecular beam. And then the molecules that come off, that's hit on that, they adsorb, and then they desorb with a cosine distribution because the sticking coefficient is 1. Some of them go back out into the vacuum chamber, but some of them see a part of the beam that's not directly exposed. And that process keeps going on, and you can load up water into the film, okay? So that's great. So looks like anatase. That's the key point here. It looks like anatase, and we can put a lot in there. So now let's do acetic acid. So for the first experiment, we're just gonna, it's kind of hard to see the color contrast here. Yeah, there's supposed to be a dark blue on gray. What we did was we basically took that particle bed and we just exposed it to a little bit of acetic acid. We didn't have the acetic acid go down into the particle bed. We heated up and we got ketene coming off. This is the temperature profiles. I didn't show you for the single, well, I guess it was there for the single crystal, but this ketene comes off, and that's a control 0 monolayers, no acetone, right? Okay. So now we go and we're just going to expose the surface to acetic acid in a temperature range where you can't build up multi-layers of acetic acid, and we're just going to increase the dose, right? The ketene comes up, 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 up. All right, that's expected, right? We've got more surface area to get more reactions. Nothing happens initially. There's very little acetone here, but for the higher doses, we start seeing acetone coming off, right? So we're getting different chemistry. It's the same system. It's exactly the same UHV system. But when we have a lot more ketene coming off, we start getting some acetone. And the supposition is that some of the ketene that desorbs from the gas phase hits another particle where there's acetic acid and its intermediates, and that drives the chemistry. The ketene yield just goes up linearly as a function of the acetic acid dose on this thick particle bed. The acetone comes up, but only after there's an induction period. You have to put enough in there. You have to give the ketene enough chance to revisit some other particle. And the acetone yield starts low, and then it starts saturating. So relative acetone yield increases as the acetic acid saturates deeper into this particle bed, right? So I didn't mention it, but we did 3 beds of particles, a thick one, the big gamish I showed you, a medium thickness one, and then a thin one. And trust me, they're all ugly when you look at them with the SEM. The thick one I've been showing you, the ketene yield for the medium one comes up and saturates because we can saturate the whole bed. Similarly, for the very thin layer of the particles, we can saturate the whole bed with acetic acid. Acetone yield for the thick bed, I showed you already. We see acetone coming off for the intermediate thickness bed, but it just saturates after a while, and then we basically saw nothing from the exposure for the thin beds. So it's all kind of consistent with this idea that we need a gas phase intermediate for these reactions to go forward. So then we did one more experiment where we took, and this was actually one of the first experiments that drove everything else. You know how it goes. It comes at the end of the story. But we made a packed pellet of these shape-selected nanoparticles, put them in a different system. It was a UHV system, but it had a little cell where we could expose it to acetic acid it was lower than we could read on the barytron gauge, 1 torr and 7 torr, and then just pump all the gas away. It goes back down to UHV or close to UHV, and do a temperature programmed desorption. You see ketene, you see acetone. Notice that the line shape for the ketene and the acetone are really, really similar, right? And the yield is kind of, in the acetone, is nonlinear in the amount of ketene that's coming off. So again, more evidence that suggests that this gas phase intermediate is playing a role. Okay, so the ketene to acetone reaction mechanism, there's this enolization step where you drop the methyl group drops a hydrogen onto the surface. You cleave the hydrogen bond there too, or I'm sorry, it's a OH cleavage there, and you get ketene coming off into the gas phase. The calculations suggest that there's a stronger chemisorb state that's available. The kinetics would favor ketene desorption into the gas phase, which is what we see. I mean, we see a lot of it coming off. And then the idea is it comes in on the gas phase, it can react with another species on the surface, and you do the carbon-carbon coupling reaction, then there's a proton transfer, a hydrogen addition, and you get to this beta-ketoacid. All right, so that was all on this, that's this thing here. What was interesting about this is that all the mechanisms, the ones that are also considered to be preferred in the literature, they all end up down here, just by different routes. And there's another route here that I didn't talk about. But it looks like, so, and kinetically, the energetics are such that the pathway for this one seems to be, with the level of calculations that were done with Annabella's group, seem to be preferable, but just, right? So anyways, so with that, I'll summarize. In this part, basically, the molecular form, there's close in energy for the deprotonated form. They're kind of both there, particularly at higher coverages. I didn't really talk too much about this, as Zdeněk was doing a lot of this with the stability of the high coverage can stabilize the molecular form. The basic idea is that the bidentate takes up 2 of your titanium 5-fold coordinated sites. The monodentate only takes up 1. And so from a free energy point of view, having the whole surface covered with bitentate and then sticking the weakly bound stuff up in the next layer is not as favorable as taking some of them, making them monodentate. And then we think that ketene, gas phase ketene, should be considered as a possible alt route for these carbon-carbon coupling reactions. So with that, be happy to answer any questions, and thank you.